Welcome to the lecture series on CFD Part 2. This is lecture 29 on features of turbulent flows and approaches to their simulation. This lecture starts with a brief introduction to the main properties of turbulent flows: unsteadiness, three-dimensionality, vorticity, steering, dissipation, coherent structures, broad range of length and time scales, and Reynolds-number dependence. Next, the phenomena associated with the transition from laminar to turbulent flow regime are described: natural, bypass, and separation-induced transition. Examples from experiments and simulations are used to highlight the main features. In engineering applications, turbulence is sometimes desired, for example, to improve mixing or heat transfer, but sometimes we try to avoid it, or at least to control it, for example, to reduce noise or vibrations. Practical examples are used to emphasize the main points. Finally, the main approaches to studying turbulence are described: empirical correlations, measurement techniques, and numerical simulations. Unsteadiness is one of the most obvious and important features of turbulent flows. At any point in a turbulent flow, all variables vary apparently randomly in time. However, turbulent fluctuations are not as random as they appear. Because the velocity field must satisfy the continuity equation, for example, it must be divergence-free in an incompressible flow, variations in velocity vector components are linked to each other. The time or ensemble averaged fields are smooth and may be steady. Except for some special situations, turbulent flows are always three-dimensional. Only the time average field can be two or even one-dimensional. Turbulent flows contain a high level of vorticity. Vortex stretching is one of the primary mechanisms by which the turbulence intensity is increased. Steering is another very important feature of turbulence. Fluid parcels from different locations are brought into contact by turbulent transport. This process is often called turbulent diffusion, although the transport mechanism is convection. Mixing takes place eventually by molecular diffusion, but the process is much more intense in turbulent than in laminar flow because turbulent steering increases local gradients. The kinetic energy of the flow is reduced by turbulence because mixing is a dissipative process. Some energy is irreversibly converted into internal energy of the flow, that is, heat. Coherent structures are repeatable and essentially deterministic events which are responsible for a large part of steering in a turbulent flow. Their number differs from flow to flow. They differ from each other in size, strength, and interval between occurrences. Turbulent fluctuations span several orders of magnitude in both time and length scales. This makes direct numerical simulation, called DNS, in which all scales are resolved, very difficult because extreme computing resources are required. Reynolds-number dependence of time and length scale ranges in a turbulent flow is one of the greatest challenges for the simulation of such flows. With increasing Reynolds number, the range of scales over-proportionally increases, and thus also the required resources for simulation. Thus, in practical applications, direct numerical simulation is limited to a lower range of Reynolds numbers. Let us now briefly discuss how a flow becomes turbulent. In most cases, the presence of a wall with a boundary layer building along it is responsible for the transition from a laminar to a turbulent regime. Boundary layers usually cannot be maintained laminar over too long distance. There are three ways of transitioning in a boundary layer from laminar to turbulent. One is the natural transition, in which instabilities in the boundary layer become amplified and develop into turbulent spots that grow further downstream, leading eventually to a fully turbulent flow. Another possibility is the bypass transition. An initially laminar boundary layer becomes turbulent when the free stream away from it is turbulent. Disturbances from outside propagate into boundary layer and lead to it becoming turbulent. The third possibility is a separation-induced transition. A laminar boundary layer separates from the wall because of an adverse pressure gradient. Shear layer instability leads to turbulence, which grows into the boundary layer at turbulent reattachment. Natural transition is the most difficult one to predict because it takes place over a relatively long distance. Transition from laminar to turbulent flow regime is also sensitive to wall roughness, sound effects, free stream fluctuations, etc. The transition of a boundary layer from laminar to turbulent regime creates first turbulence spots like the one shown in this photograph from an experiment. These spots start appearing and disappearing at one location, but when they reappear further downstream, the boundary layer becomes fully turbulent and stays turbulent. A typical turbulent spot is shown in this photograph, surrounded by a perfectly laminar flow at its sides. We see growing instability in this zone before turbulence occurs and a decay further downstream. The side view also highlights the growth and decay of turbulent structures. This animation shows a direct numerical simulation of bypass transition in a boundary layer. Free stream turbulence interacts with an initially laminar boundary layer. Low frequency modes lead to streaks. High frequency modes trigger instability, leading to turbulent spots and eventually fully turbulent boundary layer. Shear layers are zones of high velocity gradients between two streams with different velocities. Examples are jets, separation zones, and wakes behind black bodies. Shear layers become turbulent because of a growing Kelvin-Helmholtz instability. This figure shows a round jet flowing out of a nozzle into a quiescent fluid. Initially, the shear layer is smooth and the flow inside jet is laminar, but then ring vortexes build up in the shear layer and further downstream they burst into a turbulent jet. This figure shows flow through a grid with rectangular openings. We see how the flow squeezes into the openings and how the jets downstream of the grid mix to create a fully turbulent flow. The instability starts again in the shear layer, and after a short distance, the laminar core of each jet disappears. The animation shows the component of the vorticity vector orthogonal to the section plane from the large eddy simulation of flow through a grid with slightly larger openings than in the experiment shown in the upper figure. The jet cores are a bit longer than in the previous picture, but they all break into a nearly homogeneous turbulence further downstream. The animation also shows the turbulence decays with distance due to its dissipative nature. However, when the wall of an airfoil is encountered, turbulence is again generated in the boundary layer on both sides of the airfoil. These plots show transition of turbulence in the shear layer after laminar separation from a sphere at different Reynolds numbers, based on far-field velocity and sphere diameter. Ink was injected into water through two holes in the sphere, one at 70 degrees and one at 110 degrees from the front stagnation point, to visualize the shear layer and its separation. The same pattern is visible at all Reynolds numbers, but the structures become smaller as the Reynolds number is increased. The Kelvin-Helmholtz instability develops in the shear layer, leading to its roll-up, thus creating vortex rings. The first two vortex rings appear to be still laminar, while the third obviously breaks into turbulent regime. At a sufficiently high Reynolds number, turbulence from the shear layer starts interacting with the wall, leading to a small recirculation bubble between laminar separation and turbulent reattachment. The turbulent boundary layer stays attached to the sphere wall for a while until the adverse pressure gradient causes turbulent separation. This happens around Reynolds number 300,000, leading to a sudden reduction in drag and a shorter circulation zone in the wake. This sequence of pictures, 1/500th of a second apart, shows the phenomenon of vortex pairing, which creates a coherent structure that disturbs the semi-regular pattern of Kelvin Helmholtz instability at the Reynolds number of 50,000. Instead of moving downstream at a similar speed to the vortexes ahead and behind, as shown in the previous slide, one vortex stays at about the same place, waiting for the next one and embracing it. These events happen repeatedly, but not at the same distance in time. Flows in pipes and channels stay always laminar for Reynolds numbers below approximately 2000. If disturbed, the flow may become turbulent, but it returns to a laminar state after disturbances die out. Flow can stay laminar even for much higher Reynolds numbers if disturbances are kept away. Experiments with laminar flows in a pipe at Reynolds numbers up to 100,000 have been conducted in a controlled environment. However, at Reynolds numbers higher than critical, any disturbance can trigger transition to turbulence, and the flow then stays turbulent even if disturbances go away. These photographs show the famous experiment by Reynolds. Dye is injected into water flowing in a pipe, and for Reynolds numbers below critical, the flow is laminar and steady. Dye diffuses very slowly into water, so slowly that the streak line appears to have a constant diameter. At Reynolds numbers close to critical, the streak line becomes wavy and unsteady. At still high Reynolds numbers, the flow becomes turbulent and steers the dye across the whole pipe. Direct numerical simulation, that is, solving the Navier-Stokes equations using sufficiently fine grid and time steps, also produces a turbulent flow in a pipe at Reynolds numbers above critical. The parabolic velocity profile, which can be obtained analytically from the Navier-Stokes equations for laminar flow, satisfies the equations for any Reynolds number, but numerical solutions contain sufficient disturbances through round-off and iteration errors, which trigger transition to turbulence unless viscous damping at Reynolds numbers below critical is large enough. Disturbances in experiments come from various fluctuations and vibrations. Before turning the attention to engineering applications, a few statements about coherent structures are appropriate. Coherent structures are partly deterministic. They account for a relatively small amount of energy in the flow, but they are usually responsible for a large portion of transport in turbulent flow. Coherent structures are characterized by strong vorticity. They are mostly due to mean strain in the flow. Coherent structures are different in each flow or region of it. They are highly problem dependent and hence difficult to model. They are also changing all the time, being created, evolving, and eventually being destroyed. Most often they can be seen as vortexes, as in slide 11. Sometimes turbulence is desired in the flow primarily for two reasons. When good mixing is needed, for example in mixing vessels, because turbulence steers the fluid and makes mixing far more intensive than what otherwise happens by molecular diffusion in a laminar flow. This is especially important in chemical and process engineering, for example, to mix fuel and oxidant or to mix other reactants. When good transfer is needed, for example in heat exchangers, because turbulence enhances the exchange of heat between fluid and walls. Turbulence moves fluid parcels across the flow and thus brings high-speed fluid more often closer to walls, where they can pick up heat and transfer it away from wall. At the wall itself, heat exchange between wall and fluid still takes place by conduction as in laminar flow, but the temperature gradient directly at wall is much higher in a turbulent than in a laminar flow, hence leading to a higher heat transfer rate. The same is true if the wall is cold and fluid is hot. Turbulence is therefore important in heat exchanges of almost all kinds. Turbulence is also desired when separation should be delayed. Separation delay is achieved because turbulence brings high momentum fluid from outside layers closer to wall, thus increasing the mean velocity in the boundary layer. Fluid in the boundary layer can thus flow longer against adverse pressure gradient. The consequence is a delayed separation and a lower drag. The well-known example is the drag crisis for sphere. See the next slide. To achieve the desired effect, turbulence is often promoted. There are several possibilities to enhance the turbulence in the flow in a favorable fashion. For example, by using surface roughness or otherwise structured surface, like dimples on a golf ball. By boundary layer tripping, applying local roughness or trip wire, for example when doing experiments in model scale to achieve similarity with full-scale flow features. Or by installing specially designed obstacles, often called turbulators, for example on airplane wings, designed to keep the boundary layer turbulent and prevent or postpone separation. These two photos show the flow around a sphere at the Reynolds number of 50,000. The surface of the sphere on the left is smooth. It is a billiard ball, while on the sphere on the right, also a billiard ball, a trip wire is mounted at 75 degrees from the front stagnation point. The ball diameter is 61.4 millimeters and the trip wire diameter is 0.5 millimeters. The ink injected through two holes shows a laminar separation at 85 degrees from the front stagnation point in the case of a smooth sphere, with a typical Kelvin-Helmholtz instability of the shear layer and a turbulent wake. The recirculation zone behind the sphere is about 1.5 sphere diameters long. In the case of a sphere with a trip wire, the flow separates from the wire top and a small recirculation zone is formed. See lecture 31 for details from LES simulation. The shear layer after separation on trip wire becomes turbulent, and this leads to the boundary layer downstream of trip wire becoming also turbulent. The turbulent boundary layer stays attached to the sphere surface until about 115 degrees from the front stagnation point, which leads to a much smaller recirculation zone behind sphere. It is only about 1 diameter long. As a consequence, the drag is 3 times lower than for a smooth sphere. In many engineering applications, turbulence is not desired in the flow because it has negative effects on performance. It increases skin friction, resulting in higher drag. It increases pressure losses in pipes and channel networks, thus requiring more pumping power. It increases noise, because significant noise sources are turbulence-induced fluctuations of velocity and pressure. Turbulence can result in vibration of solid structures. Compromises have to be made in the optimization process with attempts to control turbulence. This diagram shows the dependence of the friction coefficient in a pipe on flow regime, laminar or turbulent, and Reynolds number and wall roughness. We see that if we could keep the flow laminar at this Reynolds number, the friction coefficient would be more than 3 times lower than when the flow is turbulent. This means that we would need much less pumping power to maintain the flow, resulting in large energy savings. We see also that at the same Reynolds number, a rougher pipe surface leads to a higher frictional resistance. Here are 3 examples of turbulence control. A classical jet engine has a smooth circular edge at exhaust, as on the left aircraft. Newer engines have so-called chevron nozzles. The perimeter is not smoothly circular but is corrugated, as on the right aircraft. The aim is to produce fine-scale turbulence at the jet edge in order to stabilize it and thus reduce both vibrations and noise. Dimples on a golf ball lead to transition of boundary layer to a turbulent state at a much lower Reynolds number than for a smooth sphere. This results in a postponed separation, smaller recirculation in the wake, and a lower drag. Thus, with the same kick, the ball flows further than if it was smooth. This photograph shows turbulence generators on an aircraft wing, designed to increase turbulence in the boundary layer and delay separation at high angles of attack. Engineers have always tried to understand turbulence and maximize its positive effects while minimizing the undesirable consequences. 3 main approaches are used for this purpose. Empirical correlations in the form of diagrams or equations have been derived which give relation between drag, skin friction, or heat transfer coefficient and dimensionless parameters like Reynolds number, Prandtl number, Rayleigh number, etc. An example is the Blasius formula for friction coefficient in a pipe, F equals 0.3164, Reynolds number to minus 0.25. These correlations work well for simple geometries like flat plates, channels, pipes, etc. However, they are not helpful for flows in complex geometries. Measurement techniques are widely used to prove design performance. For example, to verify that a new ship design meets the performance requirements at the expected power consumption. Widely used measurement techniques are flow visualization, for example, injection of dye or bubbles, tufts on walls, oil film on walls, etc. Local measurements of pressure, velocity, or temperature using instruments like pitot tube, laser Doppler anemometer, hot wire anemometer, etc. And field measurements using, for example, particle image velocimetry. Measurement is time-consuming and usually very costly. It is often limited to laboratory conditions, and the extrapolation of results to full scale is far from trivial. Since the turn of the century, numerical simulations are not only supplementing, but often completely replacing experimental studies. Numerical simulations can be divided into three major kinds. Direct numerical simulation, or DNS, requires grids and time steps that resolve all spatial and temporal variation of velocity and pressure. The requirements for computing resources increase over-proportionally with Reynolds number, approximately as Reynolds number to the power of 2.8. Therefore, DNS cannot be used as a tool for daily design and optimization studies. It is mostly used to generate detailed data instead of experiments and to validate turbulence models. This approach will be described in Lecture 30. Larger dissimulation, or LES, requires grids and time steps fine enough to resolve circa 70% of turbulence, that is, the largest length and time scales, while modeling the effects of smaller, called subgrid scales. These days, LES is used to simulate complex engineering flows, but only up to moderately high Reynolds numbers. The range of Reynolds numbers for which LES is usable increases with increasing computing power. This approach will be described in Lecture 31. The solution of Reynolds average Navier-Stokes, or RANS equations, is the most widely used approach to flow simulation in industry. The two-equation turbulence models for RANS equations from the K epsilon or K omega families, which are based on turbulent, also called eddy viscosity approach, are the main tools in daily use. Each CFD software usually offers a wide range of turbulence models, including algebraic and differential Reynolds stress models. These models will be described in detail in Lecture 32. Here is a summary of this lecture. Turbulence is one of the greatest challenges in physics. It is present in most flows of practical interest, both in nature and in engineering. Sometimes turbulence is desired, sometimes it is not. Transition from laminar to turbulent flow is important, but usually difficult to study. Engineers often try to delay or promote it. Accurate simulation of turbulence is possible. It is called direct numerical simulation. However, although it is conceptually the simplest method for the simulation of turbulent flows, it is not practical for most engineering applications due to extreme requirements for computing resources, which increase over-proportionally with Reynolds number. Engineers therefore need to use turbulence models, which are not perfect and introduce modeling errors. It is important to assess these errors, which requires knowing other errors resulting from iterative solution and discretization approximations. More details on the three approaches to simulate turbulence will be given in the next three lectures.